Okay, so now let's add the IK controls to this rig. So to spare you the time of me creating controls, I also already created the control shapes to have this kind of shape. So for the hand control of IK, we want it to be in the same position and orientation as the hand FK control, and we wanted to move with the main control of the root module. So let's add the hand control to the graph here, and the world orientation of the hand control is the hand FK guide outworld matrix. This is the oriented matrix. So if I would now directly connect the output into the offset parent matrix, we would see that this is the correct position and orientation for the control. But now we don't want to connect the guide to the control, because then it would not move with the main control. So we need to calculate another parent offset matrix. So let's make a mult matrix node and connect the guide output world matrix into the first node, and we want to have this matrix relative to the root control. And now the root control guide is at the origin of the world, so the world matrix is the offset, but for example, if it was positioned here, it would not. So again, we need to take the inverse world matrix of this guide, and this guide is connected to its output, and that is connected to the parent input, guide input. So we can take this node. Let's first refresh the input plugs. So the parent guide input, which is this node, if we take this world inversion matrix again and plug it into the second port, we now have the offset matrix of the hand IK control relative to the main control. So let's call this parent offset matrix. Oh, some illegal characters in there. Yes. And now we need another mult matrix node to actually transform the control with the main control. So we plug the parent offset matrix into the first plug, refresh the plugs, and then we need to connect it to the main control, which was connected to the output, the main output, which then again was connected to the parent input of this module. So we keep the connections to our local node. So we take the parent input node, and we take the offset parent matrix, and then we plug it into the second plug, and then we have our IK control world matrix, and then I connect the matrix sum into the offset parent matrix, and now it does move with the main control. So now I have set up the IK hand control. Maybe modify it a little bit so it's more clear to see its orientation. Let's say something like this. Okay, and then for an IK, we also, because the hand will drive the end of the IK solver, and we also need a pole vector. And for this, you can use it. You can set it up in two ways. You can use an object that floats somewhere in space, where the IK handle points to create the pole vector, or you can make a control which already is a pointy control. Scale it up a little bit, and then use one of its axes to drive the pole vector, the up vector of the IK handle. So that has my preference, but it doesn't matter in the end, but I'll set it up this way. So for the elbow IK control, we want it to be aligned with the orientation plane of the arm, so that the IK has the same orientation as the FK. So, and we used the upper guide to point in the direction of the rotation plane, and we use that to, if we look here, to set up the orientation plane guide with matrix, and we can use this matrix as a basis for the pole vector control. So if we add the pole vector control, let's just add it here for now. If we take the output of the orientation plane guide and plug it into the offset parent matrix of the elbow, we can see that the orientation, well, we have to rotate the control, but now it already has the correct orientation. We can use the negative y-axis of this control to drive the IK handle, pole vector. So we just rotate this so it aligns, maybe make it a little bit smaller. Okay, so now we have the IK control setup as well, but for some rigs it might be nice to have this control a little bit more in the position of the actual elbow, so in between the shoulder or the arm upper and the hand. So what we can do is we can add a blend matrix like this, and then we can blend this position, plug it into the input matrix, and then we can take the hand position of the guide. So that's the hand guide, and plug that into the target matrix of the bend length matrix node, and then we can set the scale, rotation and shear to 0, and then set the weight to 0.5. So now it blends half of the translation. If we now output this into the, let's expose this, into the offset parent matrix, you can see that now it is positioned in the middle of the arm. And we can as well maybe have this attribute exposed, so we can fine-tune the position according to what works best for the rig. So this is where the arm setup node, for example, comes in. If we here add an attribute, we call this maybe elbow IK blend pos, for example, make it a float, and it blends between 0 and 1. I have the default at 0.5. If we add this, and now if we take the elbow blend pulse attribute and plug it into the weight of the blend matrix node, we can now use the module setup node to set the blend position of the control. So this is the IK control guide, or IK, let's call it not control guide, because this is only the guide position. This still does not move with the rig, so we have to make it move with the rig as well, but we also want it to move with the upper arm and the hand control. So if we move the hand control, for example, we do want the position of the IK elbow control to well, stay in the middle of that position. So we have to connect the hand position to the arm IK, the elbow IK control. So to get this work, we have to do two things. We do not need the guide positions for the blending of the position of this control. We need to use the actual live or the rig transformed nodes to drive it. So let's take this and move it down to here. So instead of the hand guide that we're using for the precision blending, we are going to use the hand IK control for the position blending. So we can take the world matrix of the hand IK control and plug it into the target matrix. And then that's set up. So if we now move the hand position, you can see that the elbow control nicely blends in between. And now we have to take into account that if we move this, this doesn't work correctly, because now it's still blending between the hand IK control and the guide. So we have to take this guide and make a new matrix that has this orientation and offset relative to the main control. So again, we make another mult matrix node, and we take the incoming connection from the oriented guide plane, the oriented plane, and we plug that into the first plug of the matrix. And then we refresh the nodes for the plug to show up, and then we take the world inversion matrix of the root control guide to get the relative offset to the orientation plane matrix. So let's take the parent guide world inversion matrix, because that's connected to the guide of the root module. And now we have the parent offset matrix for the orientation plane matrix, and now we have to animate it or transform it along with the root control. So we do another mult matrix node, and then we plug in the offset, and then we take the offset parent matrix of the parent input, because that's plugged through to the root main control. And now we can take this output and plug it into the input matrix. And now nothing changes, so that's always nice. And now if we change the root control, you can see that the guides or the controls nicely follow along, and the elbow IK control blends in between. So that's set up. Then let's correctly name these. So let's call this world matrix. Sorry, this is the parent offset matrix, and this one is the IK world matrix, but we're going to blend it, so we're going to call this the base. And this is not the guide anymore, because this is actually the world matrix of the IK control, because it is dependent on the transformed controls of the main control and the hand IK control. So now we can still blend the position with the setup node and determine what's better for our rig. Where we have it. Okay, so that's the controls. Let's add these to the controls group of our module, and then now add the IK joints. So for this, we're just going to create 3 joints. Doesn't really matter where and how long, as long as their orientation is okay, like the next one is in the X direction of the parent joint, and the joint orients are all zeroed out, because we don't want the joint orient, we all want it to be 0. And let's call this the joint, the upper IK joint, the lower IK joint, and the left hand IK joint. So for the joints, the position of the hand joint will be driven by the AK handle. The position of the upper will be driven by the rig, and then the rotation will be driven by the IK handle, IK solver. So let's just plug in the initial position of the FK control, because it has the correct position, and the orientation doesn't really matter because the IK handle is going to drive the orientation. So let's look at where the IK handle or IK control gets its world matrix from. And that's in this world matrix node, so we can just take the matrix from here and plug it into the offset parent matrix of the joint, and then the joint is already at the correct position and initial orientation of the arm. So if we were to change the rig, the joint orientation of the upper would follow naturally. And now we have to set the length of these joints, and the length can be derived from the length in between the guides. So if we create a distance between node, and we have to press the show all attributes to get all the attributes to show up. So what we can do, we can simply take the guide matrices, plug them in, and the distance between them will be the length of the arm segments. So if we take the upper guide world matrix and plug it into the first matrix of the distance between, and then the lower guide world matrix and plug it into the second, we get the distance of the upper arm. So let's call this left arm upper length, like this, and then let's duplicate this, and let's call this one the lower length, and we do the same thing. We take the lower guide world matrix, plug it into the first matrix, and then we take the hand world matrix, plug it into the second, and then we get the distance between those two. And now we can take the distance of the upper length and plug it into the translate X of the lower arm, because that's the length of the upper arm. And then we can take the distance of the lower length arm and plug it into the translate X of the hand. So now the joints have the correct length, and even if we reposition the rig, the joint length will correctly adjust. Of course, the orientation of the other joints is not correct because the IK solver is not in yet. So let's add that now. So we go to a skeleton IK handle, and we're just going to use the rotate plane solver and enable snap. Well, you can disable it or enable it if you want. So we just use the default basically. Select the upper joint and then the hand, and then the IK handle is created, obviously in the wrong position, but we're going to fix that. So, and this is going to be the arm left effector, and the IK handle is going to be the arm left IK handle. Okay, so now the IK handle needs its position driven by the IK control. So for now we can just set the translation to 0 and just plug the world matrix of the hand control into the IK handle offset parent matrix, because this as well is based on a transform node and has all the appropriate plugs and matrix functionality. So you can see it has all the same matrices plus some extra, because the solver had some extra matrix plugs you can use for the orientation or up vectors. Oh, sorry, wrong button. So let's take the hand IK control world matrix and plug it into the offset parent matrix of the hand IK control. Voila. And now the IK solver follows the hand IK control. The only thing that you have to be aware of, that if you use the offset parent matrix plug for the driving the IK handle, if you set a position and undo, Maya does not always update correctly. I'm not sure why I can't reproduce it now, but believe me, sometimes maybe it's fixed in this Maya version, but in all older versions, Maya only updated the IK handle if one of the translate plugs was dirtied or changed. So for now it seems to work, so we'll leave it. But if that happens, if you undo your changes of the control positions and the IK handle does not update, you can just create a bogus connection from any node to this one of the translate plugs, and then the update will work fine if you undo the transformation. Okay, so now we have the IK handle driven correctly. Now we have to set the pole vector. So the IK handle has a pole vector. You can set it directly to any position. But as you can see, if we set the pole vector to the y-axis, which you would expect to be up in the world, it points in the backwards direction. And that's because this vector is multiplied by the parent matrix of the ARM IK handle. The ARM IK handle is in the root space, so it doesn't have a parent, but still it has an offset parent matrix plug. So now the pole vector is relative to the matrix of the hand IK control. And that's not what we want. So to fix that, we can use a pick matrix node. And if we plug the hand IK control world matrix into the pick matrix, and then we can say from this matrix we only want to use the translate. So because we only want the position for the IK handle, and then the orientation stays in world space orientation, so we can use a world space vector to plug into the up vector of the IK solver. So we will call this control out T matrix, or world T matrix. And then the output matrix we use to drive the offset parent matrix. So now you will see that the y-axis, y vector of the pole vector will indeed align it with the y-axis of the world matrix, world space. So now we can just use the control, the elbow control, to drive the pole vector or the up vector of the IK handle. So if we take this control and we want to use the negative y-axis, we have to use a matrix, vector mult matrix. It's called multiply vector by matrix. And then you can say, okay, we want to use this matrix, the world matrix of this, to multiply with the negative y-axis, so -1, and then the output vector is the vector that's multiplied with the matrix, so it's the world space matrix, world space vector. So if you plug it into the pole vector, you will see that the IK chain nicely aligns with the elbow IK control. However, this is an extra matrix multiplication or vector matrix multiplication, where we could also use the row from matrix where we can directly just get one row from a matrix. So if we want to use, for example, the the y-axis, we could just say, okay, the y-axis in the matrix notation is the second row. This is the y basis vector, so the y-axis. So we can just take the second row from the matrix, but then the arm would point in the opposite direction. So we have to flip the rotation plane. So maybe we should do that because that saves an extra vector matrix multiplication. We have another node which is axis for matrix, which basically does the same, only then you can choose which axis. You can also choose a negative axis, but then again it is negated. So we could use this and not flip the orientation plane, but maybe just for continuity we will do that. But you could use this as well instead of this. So it's a little bit faster than doing the vector multiplication, because this is just taking the second row of the matrix and then negating the values of it. And this outputs a vector 3, while the row from matrix outputs a vector 4 with the W component as well, which we will not use, but we could just directly plug the individual plugs to the pole vector attribute. So, but I want to use the row from matrix, so we're going to flip around the orientation. So in the orientation plane, we have set the axis to the negative y-axis, but we also are aligning with the negative axis of the control. So we're aligning the negative axis with the negative y-axis, so the y-axis is pointing forward, and I think I made a mistake earlier. I wanted it to point backwards, so that can be easily fixed by just setting the one of these values to the positive. So let's make this positive, then the whole rig flips, which is okay. We just have to move this along, and now the lower guide is on the wrong side, but we cannot move it to the correct side, so we have to change its limit positions or limit information. We can just say, okay, negate the negative and allow positive, so we can just change this to here, and now the controls are set up correctly, only the IK. So let's visually change this to flip to the other side, and now we have to change the pole vector of the IK, and we do that by taking the row of the matrix. I plugged this one in, but it should be this one, because this is the control itself. And now we can say this is the axis Y. We don't use this one, we don't use that one. And now we can take the output and plug it into the pole vector. So now everything is set up correctly, and we can directly take the basis vector Y and plug it into the pole vector of the IK handle. So now we still have a rig which we can adjust. If I don't select the Maya tends to take selection preference of an IK handle over a locator. So we can change the rig to any position. All the controls and the IK follow along, and the joints, the IK joints adjust as well. So we have an adjustable rig with IK and FK at this point. So let's order the nodes. So the IK handle should be in the rig nodes, because that's a node that's part of the rig internals. and the IK joints are joints, but I put them in the rig notes as well because they are not joints used for skinning. In the joints group I only put joints that are used for the skinning and deformation, and all support joints are in the rig notes. For the Maya IK handle you need joints. You cannot do it without joints. But next we'll look at a way to set this up without using the Maya IK solver and just using the law of cosines to calculate the rotation of where the IK positions should be. So we can do it without the joints and without the IK solver. But for now we use this, and then in a later segment we'll change this to a custom IK solver with nodes. So the IK chain or control that we now have, we cannot stretch the joints, so maybe let's add some IK stretching to this as well. So the joints in the arm will get longer if you stretch the arm beyond its maximum length. So for this we're going to need the actual length between the shoulder and the hand, and then if that length is longer than the upper and lower length combined, we have to scale the upper and lower length to accommodate for this length. So let's make another distance node. So a distance between, and for this we're going to need the actual position that is moving along with the rig. So that's the same as the matrix that we're using to set the initial position of the IK joint, and that is driving the offset parent matrix of the FK control. So let's take that same connection because we're going to use that position, because that is the basis position of the arm. Plug it into the input matrix, and then for the second matrix we take the volt matrix of the hand IK control. So from here, and let's call this arm left length, and then we need to add these two the upper and lower length together to know what the initial length is, or the rest length of the arm. So we do a sum, we take the distance of the upper and lower, and this is the arm, let's call this initial length. So if we need to know the ratio between the two lengths, we can just divide the current length by the initial length, and then we have the scalar. So divide node, we divide the current length with the initial length, and then only we don't want to shorten the arms when the current length is shorter, so we want to take the value, because if the current length is the same as the initial length, this output will be 1. If it's shorter, it will be less than 1. If it's longer, it will be more than 1. So we don't want it to go below 1. I call this left length ratio, and then we can use the max node, where we can say, okay, we want to use the length ratio for scaling the upper and lower arms only if it is larger than 1. So if we add another node, we can use a float constant, for example, set to 1 to plug into the second node. If you're scripting, you can just set value. Unfortunately, it's not via the interface of Maya, it's not possible to just add an input and then set it to 1. You could also not break this, because then Maya removes it. So if you're not coding, this is the only way to get a static value of 1 into the max node. But it's okay. Let's call this arm left float 1. And then this is the arm left scalar. And now we can use this value to scale the lengths of the upper and lower. The scaled length can feed into the joints. So maybe we should move this here, and then we can make a multiply node. You could also use the mult double linear, which is also multiplying two double values. But in Maya 2026, the mult double linears will be renamed to mult DL, and so because they are typed double float values instead of the multiply, which are not typed. So we'll just use the multiply for now. So we can take the scalar and multiply it with the upper arm length. And this is then, let's call this, rename this to initial length, and we call this upper arm length. And then we take the output that's going to the joint and redirect it to this output. And then we do the same for the lower. So let's rename this to lower initial length, and rename this to lower length. And then we take the scalar and the initial length, and then we take the plug that's going into the joint and plug it in here. So now we have scaled the upper and lower arm values. So if we now take the IK controller and make it longer, the arm will nicely stretch to accommodate for the extra length in the arm. So that is IK stretching.